The next test we will be investigating is called the alternating series test. Now listen to the name of it. It has to apply to an alternating series. How do you know about what's alternating? That means it's alternating between negative and positive. So you're going to see a -1 raised to a power within that series. And that's going to cause it to alternate between a +1 and a -1. The other terms, the a sub n's, should all be positive. So what does this alternating series test say? It says the series converges if the following conditions are met. Condition 1, that the limit of the nth term is equal to 0. Recall, if the limit does not equal 0, then the series is going to diverge by the nth term test and you're done. The second part is that a sub n, the terms, eventually decreases. That means it may not at first, but eventually it should. To determine if this is true, sometimes we're going to have to take the derivative of the corresponding function, because remember, when the derivative is negative, then the function is decreasing. Another big note, this test does not tell you anything about divergence. It just tells you if the series converges. So let's look at these problems. First of all, I know they're alternating series because of the -1 raised to a power. So I can apply the alternating series test. So remember, step 1, you have to take the limit of the corresponding positive terms, meaning remove the -1 to a power, and what do you have left? You have just 1 over n. What's the limit as n approaches infinity? That's 0. So condition 1 is met. Condition 2, you have to show that it eventually decreases, meaning the n plus 1 term is less than or equal to the nth term. So as n is getting bigger, the terms are getting smaller. Is that true? Well, since the numerator is the same, and let's see, this denominator is bigger. When you have a bigger denominator, you have a smaller fraction, so that's true as well. Don't need to take the derivative, very obvious. So we can just say, therefore, this series converges by the alternating series test. So show 2 conditions, and you're done. Right on the second one, so the first condition, we want to take the limit of all the positive terms, meaning remove the -1 to a power. What do you have left? You have this. As n approaches infinity, you're going to get 0. So that's the first condition. The second condition is that what happens as n gets larger. So you're going to compare the next term. So you replace n with n plus 1, and is that smaller than this? Well, again, you have a bigger denominator, but if you want to just kind of go one step further, we could just cross multiply. Remember, just being careful of that order. So we have 2n minus 1. Is that less than or equal to, and I'm going to go ahead and distribute 2n plus 2 minus 1, collecting like terms. And of course, -1 is smaller than +1, so the second condition is met as well. So once again, we can say the series converges by the alternating series test. Not difficult. Let's look at 2 more examples that look a little bit harder. Okay, so again, I know that this is alternating because of that term. This is going to be alternating because of that term. So I should be able to use the alternating series test. So again, condition 1. Remove the -1 and see what you have left. Take the limit. Is that limit 0? I don't think so. You have the same power of the same power, so you just have the leading coefficients, and that limit is 1. So we can stop right there and say the series diverges, and not because of the alternating series test. No. Why does this diverge? This is the nth term test. The nth term test. Be very careful. And you're done. Number 4. Again, condition 1. We take the limit of the natural log of 1 plus 1 over n. What's happening? As n approaches infinity, that fraction is going to approach 0. And so I'm just really left with the natural log of 1, which is equal to 0. So the first condition is met. The second one, is it decreasing? Does the natural log of 1 plus 1 over n plus 1, is that less than or equal to the natural log of 1 plus 1 over n? I have to show that. Well, you may have an argument that says this is smaller than that. So let's see. If that's true, so 1 plus a smaller number is smaller than 1 plus a little bit bigger number. So you could say, I think you could say it's true, but let's just go ahead and make sure that it's decreasing. So how can we do that? We're going to let f of x be the corresponding function of the natural log of 1 plus 1 over x. And remember, we're restricting that to be x is greater than or equal to 1 because of that index. And then I'm going to take the derivative of that function. So since it's the natural log, this goes on the bottom, and then the derivative of that goes on the top, which would be negative 1 over x squared. Ooh, let's see if I can clean that up. What if I multiply the top and bottom by x squared, just to get rid of those fractions? So I'd have negative 1. If I distribute, I'd have x squared plus x. Now remember, x is greater than or equal to 1, so that means that's always positive. And negative 1 is a constant, so negative over positive, that means that this derivative is negative on the interval x is greater than or equal to 1. So therefore, the natural log of 1 plus 1 over n is always decreasing as n is greater than or equal to 1. And so I can conclude, I'm going to come over here, that the series does indeed converge by the alternating series test. Now I know you're going, why did I go through this? Because you're going to have to do that at least on one problem on the test. So you need to make sure that you understand why we're taking the derivative. And we're showing if the derivative is negative on our given interval, then we know the corresponding sequence is decreasing on that same interval. And that's what I had to show for the alternating series test. So to conclude, the alternating series test has two conditions. You have to take the limit of the corresponding sequence and make sure that equals to 0. If not, you stop and it diverges by the nth term test. And then the second part, you have to show that it decreases, or at least decreases eventually. And if those two conditions are met, then you can say the series converges by the alternating series test.